Let's start. This is my second last lecture. Next week is the last lecture. So last Monday, we talked about supply independent reference. So I hope the key takeaway is that we need to find something that is well known and then use that to form the reference voltage or reference current. So some of the good choice of parameter including like the diode VD 0.7 volt, the VBE of the transistor BJT also 0.7 volt, or the threshold voltage of the MOSFET, although it's not well known, but we know it's constant, right? Or the Zener breakdown diode, it depends on what Zener you're using, so on and so forth. And then we talked about a very important circuit block called band gap. So band gap is very popular. If you want to sell circuit or commercial circuit, you will see that a lot of commercial circuit will have this band gap reference. Because if you think about that, one of the wonder of circuit is that regardless of the supply voltage, usually is a range, right? From let's say 3 volt to 5 volt. Or it doesn't matter what is the temperature and what is the current, somehow the circuit will still work. And one of the key block is actually this band gap reference. Because it's totally independent of the temperature, independent of the supply use, it will always provide you a fixed reference. Okay, so that is one of the very key building block. And then there is other biasing like constant GM, reciprocal biasing. These are important technique, important circuit technique. We didn't go into very detail. If you are interested, you go to the literature, you will see a lot. Constant GM, I think some students feedback to me that industry people is not using it. I'm not too sure, but I do read the paper. Constant GM, people use it because they can form the gain in a fixed ratio. I show it to you already. And reciprocal bias is a very important technique that popularly used in a lot of literature, reported literature, and also commercial product. And then we try to wrap up the whole session touching on the concept so-called gain bandwidth product. The key takeaway is that gain bandwidth product, you need to know there is a trade-off. So a lot of time we trade off gain with bandwidth. We lower the gain in order to get wider bandwidth. Okay, so it's a very key, important parameter. And for a lot of technology, you will see that a very key, important parameter is called unity gain frequency, FT. And I hope you still remember my advice is that if you know the FT of the technology, usually you can sort of deduce what kind of operating frequency range the technology is good for. So if the FT is, let's say, 100 gig, you know that circuit should be no problem designed all the way up to 10 gig. So usually it's 110. Okay, 110. Some of you probably object saying that, no, I have seen FT that is 60 gig, but people are designing 60 gig. That could happen if you have some passive network like inductor, okay, that help you tune out the capacitance. So then you can actually widen the bandwidth. And then we talk about frequency response. The thing is that why do we need to know frequency response since nowadays everything is computer generated? You can easily figure out the magnetic response, phase response easily using computer software. Now the thing is that sometimes you don't want to run the simulation just to figure out whether it is right or wrong. Okay, this happens a lot. When you look at the report generated by your teammate or the simulation result generated by a team of engineers, how do you know that they are doing the right thing? You don't want to go back, check their work, rerun the simulation yourself, and then just to comment whether they are right or wrong. So knowing how the frequency response looks like, that can help you decipher or look at the work or deduce whether the work is right or wrong in a very quick manner. And then eventually we stop at stability. I think the only thing we mention is that a stable system always have left half plane pole. Okay, and today we are going to further explore this topic. So we'll talk about how come the left half plane pole zero concept come about. Okay, and more importantly, how do we determine a system is stable or not stable? To be frank, you can consider circuit as a subtopic of control. In fact, all this stability, all this frequency response compensation has been well covered in control system. So if you have taken control topic before, all this topic is not new. Okay? Control emphasizes a lot on the feedback system. So when you have negative feedback, you always have this stability issue. So they will look at the whole closed loop system. They will look at the stability criteria. They will talk about body plot, so on and so forth, phase margin. All these topics has been covered in control theory. And given circuit is part of the system, okay, so we borrow or we leverage on this concept taught in control. We brought it here. There might be some subtle difference, but the key thing is still borrow from the control theory. So if you have some issue understanding, I would recommend you to go back and take a look at control theory. Okay, control theory, I think undergraduate you should have taken some of the topic related to control theory. I'm not sure whether that is true. Have you guys taken any module related to control system? Never? You have never learned about body plot? Stable system, left half plane pole? Never? You don't look at the system at all? That's strange. Now, first of all, I think system, we don't even talk about control. Signal and system. In NUS, that is second year module 2023. We'll probably talk about system, and then we'll talk about transfer function. We'll talk a little bit about the stability, okay, the response, so on and so forth, second order system response, and the body plot. I think we'll talk about that. And this is actually sort of the common knowledge that EE should understand. Okay, because we always build system. Anyway, after we talk about the stability criteria to know or analyze how a system is stable or not stable, we are going to go beyond. If a system is unstable, how do we make it stable? So that involves the concept called compensation. Compensation. And there are three different ways of compensate a system if it is unstable. The simplest one is called lag compensation. Simplest one, very easy, understandable, but not that good. Meaning that it can make the system stable, but you end up having a very low bandwidth system. Okay, low bandwidth system, so it's not high speed. The lead lag slightly better, lead lag. So a bit more complicated, but the good thing is that you are able to achieve a much wider bandwidth for your final closed loop system. And finally, we go even more ambitious, lead compensation. So not only we try to make the system stable, we are going to make the system so stable that the phase margin is even beyond what we can dream of. Okay? And that will actually lead to even wider bandwidth system. And of course, we keep talking about bandwidth. Why? Because bandwidth directly related to settling behavior. Okay? So a rule of thumb, if you want to settle fast, let's say you have a bandwidth of omega. So the settling time usually is 6.9 divided by omega. Okay? A very simple rule of thumb. Why 6.9 over omega? Omega, you can think of it like a RC time constant. Omega for a simple passive low-pass filter is 1 over RC. Right? And 1 over RC is the time constant. So if you have a step response, how long does it take for the RC to settle? Settle to 99.9%, it takes 7 RC or 6.9 RC. Okay, so that is how the link between the bandwidth and the settling behavior. So finally, we introduce a concept called doublet. Okay, it becomes clear to you what is doublet. And finally, bandwidth is not the only thing that determines settling behavior. We have another thing called slew rate. Okay, very strangely, later you will see. The slew rate behavior seems to be linear because the time is linearly increasing. But we call this behavior nonlinear behavior. Okay? On the other hand, the bandwidth kind of thing, if you know, the settling is actually exponential. Although it's exponential, but we call this kind of settling behavior linear settling behavior. It's kind of confusing, okay? But the reason why? Because the settling behavior is related to linear system. Linear system. On the other hand, this slew rate happen because when that is happening, your system is no longer considered as linear. It gets saturated. A system gets saturated, usually it's nonlinear behavior. So we call this kind of settling behavior nonlinear behavior. Okay, there are many ways of looking at the stability. A very simple way, if you look at the system transfer function, if you are able to factorize the denominator, meaning finding the roots of all the denominator. Okay? Now, if you are able to find the roots for all the denominator, it means you can find all the poles of the denominator. So if you are so good at the mathematics, or if you are so good with MATLAB or whatever, you are able to do that. And you find that all the poles fall under the left half plane. Left half plane meaning the negative axis, negative sigma axis. If that is the case, we can conclude the system is always stable. Okay, so we simply look at the pole, look at where is the location. If they all fall under the left half plane, this is stable. Simple as that. So that is very easy provided you know how to factorize the system. If you don't know how to factorize the system, you are doomed, because you don't know whether the pole is on the right or on the left. Right? So the first principle is very simple to understand, very easy to realize, to judge. But that is provided you are given the system that is already being factorized. But a lot of time, you know, the system cannot be factorized nicely. So if that is the case, in fact, the second and the third method is actually easier. So in the second method, we call the Nyquist stability criterion. What you do is you plot the loop gain. You plot the loop gain. We will talk about loop gain later. Let's assume the loop gain is called Ts. Okay? You replace the S with the j omega variable, and then you try to change the omega. You change the omega from negative infinity all the way to positive infinity. Meaning you change the frequency from negative frequency all the way to positive frequency. And then what do? You try to figure out at each point what is the magnitude, what is the phase. So once you find the magnitude and the phase, you can start plotting the root locus. Okay, or the locus. I wouldn't say root, the locus. When you start plotting the locus, you'll see that there is a plot being generated. And to judge whether it is stable or not, as long as the plot encircles the -1, 0 point, we conclude not stable. But if it doesn't encircle, we conclude stable. Now, later I'm going to illustrate with the drawing that it becomes clearer. Now, this method sounds complicated because you have to change omega all the way from negative infinity to infinity. And you have to plot the magnitude and the phase. But it's simple in the sense that you give me any system, I can always do. I don't have to factorize. Because any system in terms of S, I can always replace S with j omega, and I just have to substitute omega inside. I can figure out everything numerically. You get the point? I don't need a lot of mathematical skill. I can even create a very simple program, just plot. I just run omega from negative infinity to infinity. I try to determine what is the complex number, resulting complex number, so I can get the magnitude and the phase, and then I generate the plot. So very easy to do. Although the procedure sounds complicated, but it's very easy to do. And the judging criteria, very simple. Okay? Now, this is good in the sense that it frees you from the capability to factorize the system. You don't need to know whether the pole is left half plane or right half plane. You don't even need to know where the pole is. You just have to substitute and calculate. So the second method is very simple. But the problem with second method is that that's it. It describes a step for you to do. But after that, what can we do? We already judged the system is stable or not stable. What can we do? Nothing much. So it's very good tool for you to evaluate the system stability. But after that, nothing much you can do. That brings us the third tool, body plot. So body plot, actually, if you think carefully, later I'm going to illustrate, it's actually originated from Nyquist. It's based on the Nyquist understanding of stability. Okay, we just extract key point. One is when the gain equals to 0 dB, what is the phase? Another is when the phase is 180 degrees, what is the gain? So that brings you the so-called phase margin and gain margin. Okay? It's actually a subset. You actually look at the Nyquist plot, and then it doesn't care about whether encircle or not encircle. It just look at 2 points. And from that 2 points, it can deduce whether it is stable or not stable. But not only that, it actually gives you a sense. If the system is stable, how stable it is. If it's unstable, how unstable it is. And then it actually allows you to, based on this guy, to think of a way. Can we somehow manipulate the system such that, let's say originally the phase margin is 45, can we make it become 60? Or if the system originally the phase margin is minus, which is unstable, can we make it becomes positive? So it actually gives you a way to think, how can we make the system stable or not stable? Okay? So all these three methods we are going to talk about. The first method, we always say left half plane pole. All the stable system can only contain left half plane pole. Why? So any system can be described using transfer function HS. You always have the numerator, you always have the denominator. And it doesn't matter whether it's numerator and denominator, if it's a polynomial, you can always factorize. You can always factorize. So as shown over here, you can factorize doesn't mean you are able to factorize. You get my point? Mathematically, you can prove that I can always factorize a polynomial system. But whether you can do it on the spot, that is a different story. Okay? I give you any polynomial, can you factorize? Not necessary. But are you able to find is there any solution? There is. Definitely there is. But are you able to find it? That is a different story. Okay? So I assume not only there is a solution, you can find it, then I can rewrite the polynomial in all these bracket terms. So the numerator will be consist of all the polynomial like s minus z1, s minus z2, s minus z3, so on and so forth. In terms of the pole, it will consist of s minus p1, s minus p2, s minus p3. And from mathematics, we know. The good thing about factorizing is that we can separate them. After you factorize the denominator into multiple factor, I can separate them and consist of the individual term. Like this guy. You know about this, right? In performing the integration, this is one of the techniques that is taught to you. I give you any fraction, polynomial fraction, try to find the integration. What do? You factorize it, separate them into individual one, and then when you do the integration, as long as the denominator only consists of s minus p1, if you integrate, it becomes ln. Am I right? So this is one of the very simple way of doing the integration. But this is Laplace transform we are talking about. Okay? So if you are able to factorize the system into the following form, to know how the system responds, we have the concept so-called impulse response. Have you heard of the term called impulse response? It's basically a system, you send it an impulse, which is a delta direct function, and then you observe the output. Okay? Now, that is what we call impulse response. Now, to find the impulse response is basically finding the inverse Laplace transform of this guy. So, inverse Laplace transform of this guy. Finding Laplace transform, you know, right? Finding inverse Laplace transform, just reverse. Now, we don't need to perform all this integration. We actually, mathematician has already do that and tells you if there is a state response, the Laplace transform is 1 over s. And therefore, inverse response is a ut, a state response. Right? And then if there is a delta, like this guy, delta direct function, I think it becomes a constant. Okay, so on and so forth. And then there are other things like 1 over s, actually s, 1 over s minus something. If you look carefully, all it means is actually exponential function. And for this exponential function, you notice one thing. This exponential function would increase with time if p have a positive real part. Okay, so you end up having this guy, positive real part. But if there is a negative real part for this P, then you are having an exponential decay system. And that is the reason why we say a stable system always have left half plane pole. Because once you have left half plane pole, it means you always have negative real part. Okay? You always have negative real part. So this is so-called sigma. This is called so-called J omega. So if sigma is negative, which is this guy, sigma is negative, you always have negative real part. And therefore, you either get this guy or you get this guy. A system that after you excite it using a delta direct function, it go down to 0. That system is stable, right? No matter how you excite it, it doesn't stay long. Eventually it will decay and go back to 0. This system is stable. But if you excite it, it grows exponentially. Of course, it will not go infinity. So it grows exponentially, eventually it will saturate. This is oscillator behavior. It means after you excite it, it will start oscillate. So this is unstable system. Okay? Now, of course, we already covered. All these depend on whether you are able to factorize it. If you are able to factorize it, you can easily plot out the pole. Okay? And as long as you see the pole falling under the right half plane, you know this is unstable. If all the poles fall under the left half plane, then this is stable. Simple, but not easy to do. So Nyquist theorem described in this manner, what does it mean? So supposedly, you have the closed loop transfer function look like the following. Okay, look like the following. You are going to not plot out the whole transfer function. You just focus on this guy over here. You just focus on this guy over here, which is 1 plus aj omega f. And in fact, we can lump this guy and call it tj omega. So basically, it's plotting 1 plus tj omega. How do you plot it? So as I mentioned, you are able to find the pole, you are able to find the 0. You can then actually figure out, when you substitute the omega, what it means is basically, let's say I take this point over here. I am finding the magnitude for 0, okay, and the magnitude for pole. I also find the angle. Right? So what I do is basically, I'm finding the magnitude due to ZRI and the phase due to ZRI. Okay, theta. And then I have another one, which is magnitude due to ZLI and the angle due to ZLI. And then I divide by magnitude due to pole I and the angle due to pole I. Finally, I can lump it and form a magnitude total and the angle total. Okay? So suppose I'm having omega at this point, let's call it omega 1. So after finding the omega 1, I obtain a certain magnitude, a certain angle. So I will plot it. This will be my magnitude total. And then this will be my theta total. You get the point? Okay, so that is how I plot for one particular omega I point. Now if I move omega further, I will get different magnitude, I will get different phase. Now here I'm illustrating the principle using the 0 and the pole. But in reality, do I really need to know the pole and 0? I don't need to. I just substitute the omega into the whole transfer function. I can figure out the magnitude and the phase, which is the total one. I don't need to find individual pole, individual 0. Okay, so that is the beauty of it. I don't need to factorize anything. If you keep doing that, okay, when omega is bigger than 0, if you keep doing that, they will actually go clockwise in this manner. Now if you go omega equals to negative, you actually go in this manner. Okay, so that is how you plot And we call this guy locus. Okay, we plot the locus. Now if we plot this one, then we judge. Does it enclose this point? Obviously in this system it doesn't, right? After you plot everything out, you see that, oh, my figure, my final plot doesn't enclose this origin 0, 0. Since it doesn't enclose, we conclude the system is stable. Okay? If it encloses, the system is unstable. Now, I didn't go through the theory behind, but it's actually quite simple to understand. When would this guy becomes unstable? When this thing becomes 1 plus ASF equals to 0. Am I right? If the denominator becomes 0, the whole thing becomes unstable. That is the origin. Okay? So if you guarantee that whatever that you find actually doesn't enclose this guy, then the system can be proven is always stable. There is a whole bunch of mathematics behind this theory. I'm not going to go through the detail, but it's sufficient to understand. We just use it. If you plot the Nyquist root locus and then you do that, you see whether it encloses 0 or not. If it encloses, then it's not stable. If it doesn't, it is stable. But it's kind of a nuisance. You always have to plot 1 plus something. So if you think carefully, do I need to include the 1? I don't need, because eventually I'm interested is only Tj omega. Okay? So let's just plot Tj omega. Let's just plot Tj omega. So this is wrong, huh? Please remove this guy. So let's just plot Tj omega. Oh, no, sorry. I make a mistake. Forget it. Forget it. I make a mistake. Now this is just to illustrate. If you do the same plot and you find that this whole system actually encloses a 0, the origin, you conclude this system is actually unstable. Okay? So comparing these two plots, you know that this is stable, this is unstable. But as mentioned, always plotting with this one is kind of nuisance. Okay? All the calculation, we always have to include this one. So we can actually just focus on this guy. Or equals to Tj omega. Think carefully. If I plot 1 plus something enclosing 0, now let's say I remove 1. I remove 1. This addition of 1. Effectively, I'm no longer looking at enclosing 0. I'm looking at enclosing minus 1, 0. You get the point? It's like, instead of plotting this guy, so now I start plotting, shifted the axis here, now I start looking at this point, it is actually minus 1, 0. You are shifting the axis. Okay? So, Nyquist plot, you can see two of them. One is plotting out the whole loop gain, 1 plus something. Sorry, not loop gain, 1 plus something, the whole denominator. Another one just focus for plotting the loop gain, which is AF, Tj omega. So here we adopt the second approach, okay? So here you can see I actually only focus on the Tj omega and I try to plot. So let's assume this system is actually stable. Whatever that I plot is actually stable. And then I know that if it encloses this point, which is 1, 0, this is unstable, this point, I would actually draw a unit circle based on this guy. So this is the unit circle I'm talking about. Now, since I know this plot is actually stable, this system is stable, Nyquist theorem only tells you how stable it is, but only tell you whether it's stable or not. But if you want to know how stable it is, there is a way. For example, let's measure how far it is away from this unstable point, minus 1, 0. So if you do this plot, you look at the blue dot over here, the blue dot over here. You measure how far this is away from minus 1, 0. Obviously, if it's very far, let's say focus on this point, this is definitely more stable than this guy. Am I right? So, you know, right, in some movie, there are those gangsters trying to drive motorbike and then see how near they can stop the motorbike at the edge of the cliff. The nearest the guy is, the bravest the guy is, and therefore he wins the competition, right? So here is the same thing. You know the edge of the cliff is the unstable one. So you measure how far am I away from this cliff. If I'm very close to this cliff, I'm very unstable. Let's say some landslide, I'll fall off the cliff, right? So very unstable. But if I'm very, very far away from this edge of the cliff, I'm very safe. So the concept is like that. So if you try to measure this, how far it is, you actually measure the amplitude. You measure this amplitude compared to the unity gain, -1. Same thing is about the magnitude. So we call this guy gain margin. Gain margin. So how far am I from 1? If I'm very far from 1, I'm stable. Okay, if I only get 0.1, that is stable. If the distance from 1 is only 0.1, that is very unstable, but the distance from -1 is, let's say, 0.9, I'm very stable. Okay, so that is what we call gain margin. And this is measured, if you think carefully, this is measured when your phase is actually 180 degrees. So the gain margin, the way it works is that you try to measure, okay, at 180 degree phase shift, what is the corresponding gain? If this gain is smaller than 1, it is stable. If this gain is bigger than 1, unstable. Now, how small it is? If it's very far away from 1, let's say I only get 0.1, I almost have 0.9 margin. That is very stable. But if I'm 0.9, very close to 1, so I only have 0.1 margin, so I'm not that stable. So gain margin gives you a way to measure how stable you are. Now, unfortunately, you see gain margin is not very popular. There is another way of measuring how stable it is. That is what we call phase margin. So the phase margin is actually doing in the other way. Instead of looking at the phase that is happen at 180 degrees and measure the gain, why don't we measure when the magnitude drop to 1? Am I very far from 180 degrees? If I'm very far from 180 degrees, I'm stable. If I'm very close to 180 degrees, I'm unstable. Okay? So phase margin is basically looking at the intercept when the gain dropped to 1. When the gain dropped to 1, then I measure how far it is from 180 degrees. The larger the angle, the better the phase margin, the more stable it is. Okay? Now, this sounds very complicated, but to understand the principle is actually very simple. We talk about these. Or simply put, 1 plus t j omega. We know this guy is unstable if it is equals to 0, or t j omega equals to -1. Am I right? What is -1? It's basically magnitude of 1, but angle that is 180 degrees. So if t j omega equals to this guy, I know it is unstable. So then the gain margin, basically, let's say I have another system that have t prime j omega. So I can do two things. One thing is, I look at the magnitude when you drop to 1, what is the corresponding angle? If this angle is less than 180 degrees, stable. Okay? Or I can look at another way. When the angle is 180 degrees, what is the magnitude? If the magnitude less than 1, stable. Okay? And better yet, these actually give us a quantity, or to quantify, allow us to quantify how stable a system is. Okay? Both ways are doable, but in circuit, you will see a lot of time we use phase margin instead of gain margin. So to summarize, The gain margin is the extra room for the feedback gain until the system starts to oscillate. So you measure how far it is from unity or from -1. The phase margin is again the same thing, extra room for the loop phase until the system starts to oscillate. So if omega k bigger than omega 180 degree, unstable. If omega k less than omega 180 degree, it is stable. In another word, phase margin bigger than 0 degree, stable. Gain margin bigger than 1, also stable. Okay? So the gain margin is measured as the magnitude response inverse. So therefore it has to be bigger than 1. Okay? And then the phase margin is measured how far it is away from 180 degree. Now, here is the simple plot. So suppose this is the loop gain. So Tj omega. Tj omega, loop gain. Now, the maximum loop gain that you can apply while the system is still stable, because we already know, as long as Pm is bigger than 0, it is stable. So the larger it can go or the smaller it can go, Pm equals to 0. So if you look at this plot, if you identify when is the phase equal to 180 degree, let's say at this point, you bring it up. So this is the frequency when the phase becomes 180 degree. Okay? When that is the case, if you look up the corresponding magnitude, so this is the maximum loop gain that you can apply to the system and expect the system to be stable. Of course, it's very delicate, very fragile, because it's 0 degree, you don't have any margin. Okay? Now, if you pick this point, the phase margin is 0 degree. Okay? The gain margin is also equals to, I think, 1 over 0. Is it? Sorry, 1 over 1. So there is 1. Sorry, 1 over 1. There is 1. So actually, you don't have any room for gain margin and phase margin. Now, suppose, let's pick some frequency. Let's pick this guy. Okay? And if you pick this guy, sorry, did I pick this guy? No, sorry, I'm wrong. Let me remove. Here the example. If I pick my omega k, my unity gain frequency, to be my second pole. So let's say I move this guy to here. Okay? I make omega k equals to omega p2. If you look down, the phase is actually minus 135 degree. So the phase margin, if you use 180 degree minus away this guy, you get 45 degree. So your phase margin is actually 45 degree. Now in terms of the gain margin, you can also look up. So if you look out this guy, there is the magnitude. And then you can see how far this is from unity. Okay? This is the unity, so you can actually measure what is this guy, and that gives you actually the gain margin. Now this is body plot. Now when we talk about phase margin, there is actually a preferred value for the phase, and we consider the system is actually quite stable. Here I'll give you some illustration. When you plot the closed loop system, you know this is complex number, this is also complex number. So you can always plot this complex number using the corresponding magnitude and the phase as follows. Okay? So assume in the example, your phase margin is 45 degree. Okay? So therefore, your closed loop function is given by this guy you just replace with this guy, and then this guy you just replace with this guy, and you get finally this thing. If you go and calculate out, this guy is going to have a peaking of 30%, 1.3. So if you go and plot this out with different phase, let's say phase margin, let's say 30 degree, 60 degree, 70 degree, and you go and plot out the function, you will see the following. The smaller the phase margin, the higher the peaking. Okay? So for 70 degree, you don't have any peaking. For 60 degree, also quite nice. Very negligible peaking. But once you go 45 degree and 30 degree, you start to see peaking. It doesn't mean the system is not stable, but the system is undesirable because it's going to have a lot of ringing. If you recall, LC circuit, am I right? How does the frequency response look like? It looks like something this, right? If you try to plot the frequency versus the magnitude, okay? So at the resonant frequency, you see the amplitude actually has the biggest peaking. So in fact, you want to avoid this kind of peaking because this peaking means that the system is prone to oscillation. It's actually very similar to the LC resonator network. You have this kind of high Q system. In fact, this is related to high Q system. The higher the Q, the larger the peaking. Okay? So you can see that now why we want to avoid peaking and why do we want to pick larger phase margin. They are all related. If you have larger phase margin, you will have smaller peaking and the system is less oscillation, less ringing, and therefore stable. They are all interlinked together. Let me see. Okay, this is in terms of log skew. Sorry. This is in terms of linear skew. So here I'm plotting using the log skew. So in log skew, it doesn't look that terrible, right? So there is still peaking, but it's only slightly peaking over there because of the log skew. So the two are actually the same, except that one is log skew, one is linear skew. Now in terms of step response, you can also run the system. Once you get the system, you just send in the step response and you see how the whole thing settles. So if you have very good phase margin, 70 degree, you can see that it settled quite nicely, almost like an exponential decay kind of thing, right? Exponential charging all the way. Now the red one, 60 degree, not that nice, but the good thing is that although it has some peaking, it doesn't ring. And it settles quite fast. You can compare these two curves, the red curve and the light blue curve. You can see that although this guy don't have peaking, he actually takes longer time to settle, right? But the red curve, you have some slight peaking, but it actually takes shorter time to settle. So there's a trade-off. We can allow some peaking in order to settle fast. But if you go further, 45 degree and 30 degree, not only you have peaking, you also have ringing. Can you see that this guy is actually oscillating? The blue one even worse, oscillating. The system is stable because you can see the oscillation die down. But we always want to avoid this kind of situation. You're probably wondering why. And as long as it's settled, as long as the system is stable, why do we care about ringing? Right? But ringing will affect your output. Okay? It doesn't just affect your output, it affects other things. Because when there's a ringing, your supply is going to be noisy, and this supply noisy is going to affect other systems. So it's not a simple thing of, I can accept the ringing as long as it's settled. It's not that simple. If it's ring, it affects the supply, and the supply affects other part of the circuit. So you always try to avoid ringing as much as possible. So what is considered as a suitable phase margin? So usually any phase margin fall under 60 to 70 degrees is considered desirable. As mentioned, 70 degree doesn't have peaking, but it settles very fast, very slow. 60 degree has some peaking, but no ringing. The good thing is it settles fast. So anywhere in between is considered good. 65 degree is what people refer to as critically damped. Bigger than 70 degree is actually over damped, meaning that the system, you introduce too much compensation. So you damp the system too much. Although it doesn't have ringing, but it settles very, very slow. Okay? If you have phase margin less than 70 degree, you don't damp the system. In fact, you damp the system insufficiently. So the system is prone to oscillation. Okay? So frequency compensation. Now consider this loop gain. We have covered OM. We know that usually you have more than 2 poles. Here we just look at the 2 poles. So one pole happen at 2 megahertz, another pole happen at 20 megahertz. Okay? If we don't do anything, the maximum loop gain that you can apply with phase margin of 45 degrees is actually this amount. Okay? You can only apply this amount of feedback. Because if you apply this amount of feedback, you're going to end up having 135 degrees, and that gives you 45 degree phase margin. Okay? If you don't do anything, that is going to be what happens. So this OM, if you target for 45 degrees, the feedback factor that you can use is only 0.01. 0.01. How do I figure that out? This is the dominant pole, 2 megahertz. This is the non-dominant pole, 20 megahertz. The slope is actually minus 20 dB per decade. So the difference in this gain is actually 10 times or 20 dB. Okay? 10 times or 20 dB. So the maximum allowed feedback is actually 10 times or 20 dB. But your whole gain, or your whole loop gain is actually 60 dB or 1000. And you want to make sure that this is the only allowable loop gain. So your T equals to your gain multiplied by the feedback factor. Your gain is 1000. Your allowable T is only 10 times. So what is your F? Your F becomes 0.01. So if you use this system in the feedback manner, the feedback factor cannot be more than 0.01. If you go more than 0.01, your phase margin is going to be less than 45 degrees and therefore unstable. Now if you do nothing, that is going to be what happened. But what if we introduce shunt feedback? So this is what we call lag compensation. Lag compensation. Sorry. Yes, one of the lag compensation. This is lag compensation, but it's not that good. So this lag compensation, very simple. You just look at the dominant pole. You try to move the dominant pole further to the left. Okay? And you don't touch the second non-dominant pole here. So let's use this amplifier as an example. This amplifier, if you look carefully, I can actually figure out 2 poles quite straightforward. The first pole, if I have a dominant load capacitance, so my first pole is going to be dominated by this load capacitance. So that is 2 megahertz. And then my non-dominant pole consists of this parasitic capacitance. And if you calculate it, this becomes my non-dominant pole. And for this system to work, we don't touch the non-dominant pole, so it remains the same, 20 megahertz. What we do, we increase CL. By increasing CL, we are making 2 megahertz drop. So we are moving the pole to the left-hand side. Okay? Now if you move the pole to the left-hand side, you'll see that this slope doesn't change. This slope is still minus 20 dB per decade. But the good thing is that now you have chance to drop all the way till here, till this point, before the phase becomes 135 degrees. Okay? By moving the dominant pole further to the left, you allow the gain to drop all the way to 0 dB before the phase becomes 135 degrees. Okay? Why we want to do that? Because it means now you are able to apply maximum loop gain. So here you can apply 60 dB or 1000 times for your T. So your T j omega now can be 1000, which means A, F can be 1000. Since your A is 1000, so it means your F can now be 1. So when you apply this feedback system, your feedback factor can actually be 1. Okay, you can apply maximum feedback factor up to 1. So here the simple procedure. We notice that for shunt feedback, the frequency ratio is exactly the same as the gain ratio. Okay, frequency ratio is exactly the same as gain ratio. So our second pole, 20 megahertz, we don't want to change, so we make it the same. I don't know what should be my first pole, okay, but I do know that these two ratios should obey the gain ratio. So what is the gain ratio that we want? So we want this gain ratio originally from this guy. Now I need to change to this guy. Let me see. 20 megahertz. Maximum gain. Oh, sorry. This is 50 dB. Sorry. So if I want to have this frequency ratio to maximize my loop gain, okay, it's basically the same as the gain ratio. So one is at 50 dB, another is actually at 0 dB. So therefore, the F2 corresponds to gain of 1, F1 corresponds to gain of 50 dB, which is 316. Using this formula, you can then figure out your F1 can be found to be 63.3 kilohertz. So if we assume 50 dB split equally between the two stages, A1 and A2, I have two-stage amplifier, A1 and A2. Okay? So each stage has about 17.8 gain. My RO2 is about 2 kilo ohm. So with this 2 kilo ohm, I can then figure out my CL. Okay, with this guy to be 2 kilo ohm, I can now figure out my CL. Instead of 2 megahertz, now you have to change this guy to 63.3 kilohertz. So this is my new CL in order to obtain 63.3 kilohertz. If you stick to the original, 39.7, we are going to end up having 2 megahertz. So this is the simple shunt feedback. You just increase the load capacitance, lower the dominant pole frequency, such that you can maximize the feedback factor to 1. Now the problem, you can see that 39.7 picofarad probably doable on chip, because we did cover 20 picofarad is actually commonly used. But once you lower it down to 63.3, your load capacitance now has to be 1.26 nanofarad. Now nanofarad, the capacitor is going to be very big. So the only way for this compensation to work is to use external capacitor. External capacitor. Another issue with this shunt method is that you can see originally I have quite wide bandwidth. By moving this guy down to 63.3, now I'm actually narrowing down the bandwidth. So this out end, although it works, but it's going to have very narrow band operation. So there are two methods associated, two issues associated with this compensation technique. One is too big capacitor, another is actually narrow band. That brings us to another kind of compensation called Mueller compensation. So still two stage, but instead of having CGD, now I purposely introduce a compensation capacitor called CC in between the first stage output and the first stage output and the second stage output. Okay. Now, if we calculate the dominant pole is no longer CL. The dominant pole is actually due to Mueller effect, this CC. So you can see CC multiplied by the amplifier gain of the second stage. So the capacitor becomes very large. And then you multiply by the first stage output resistance. So this becomes your dominant pole. And then your non-dominant pole, we covered that last week. You can consider short circuit. So if you short circuit, now you have this capacitor and this capacitor add together. And then you are going to have this diode connected transistor, which is 1 over GM2. And that becomes your second non-dominant pole. Now, of course, due to this feedback, you have this additional right half plane 0. This right half plane 0 will introduce phase shift. And right half plane 0 happen at this frequency, GM2 over CC. Now, conceptually, using Mueller compensation, you also have the same effect. It's trying to move the dominant pole to the left. But the non-dominant pole, instead of making it remain constant, it actually moves this non-dominant pole to the right. Sorry, wrong. Right over here. Move the non-dominant pole to the right. This is what we call pole splitting effect. I think last week, if you remember, I show you that if you have two poles, okay, if you introduce something to the loop gain, one pole will move to the left, okay, another pole will move closer to the j omega axis. Pole splitting. So this referring to the dominant pole. This referring to the non-dominant pole. Okay? Now, the good thing compared to shunt compensation is this. You can see the pole splitting. This guy moving over there is trying to make sure the gain drop. Okay? The gain drop faster before I reach the phase of 135 degree. But this guy moving to the right is telling you my phase is going to drop to 135 degree at wider frequency, at higher frequency. Okay? So combining these two effects is telling you you don't have to move all the way to the left, unlike the shunt method. Because at the shunt method, the 135 degree is fixed. If 135 degree is fixed, I have to move this certain amount in order to reach 135. But now if this point is moving to the right, effectively, this point can also move to the right. So the good thing about this is, I don't have to move this all the way to the left, because my 135 degree also gets shifted. So in that manner, I can actually achieve wider frequency compared to the shunt method. If you think carefully, when you don't need to move the dominant pole further to the left, you actually have higher frequency. Okay, wider band operation. Now, how do you choose the CC in order to get the phase margin that you want? So, simple method. You look at the final phase contribution. The phase, this guy is going to contribute certain phase. This will contribute certain phase. This will also contribute certain phase. So if you look up the expression, this is the total gain. Now the bandwidth, because of the Mueller effect, this is the new bandwidth. So the gain bandwidth product, if you multiply the two, this becomes your unity gain bandwidth frequency. Now phase margin for the unity gain bandwidth frequency, phase margin is measured how far your phase compared to 180 degree. So therefore I use 180 degree. The first phase contribution by the dominant pole is given by this guy. The second phase contribution from the non-dominant pole is given by this guy. And the zero also contribute phase lag, because this is actually right half plane 0. We covered that last week, telling you right half plane 0 also contribute phase lag, not phase shift, phase lead, phase lag. So you have actually 3 negative components here. Okay? Now unity gain frequency usually is very big. Okay, unity gain frequency, where is it? Somewhere here. So it's definitely very big compared to this guy. Okay? But it might not be very big compared to the non-dominant pole and also 0. But it's definitely very big compared to the dominant pole. Now, if up tangent, this guy is very big, much bigger than omega P1, you are having omega K much bigger than omega P1. You can consider it like up tangent, almost infinity, right? That will give you 90 degree. So therefore, this term actually contribute to 90 degree. So 180 degree minus 90 degree, you end up having 90 degree. Now let's look at the two other terms. This guy, unity gain frequency, we can use this thing, omega k. Your omega p2 is given as follow. Okay, so you can actually substitute. Omega k is given by gm1 over cc. Omega p2 is given by this guy, so gm2 cgs plus cl. Now cgs is parasitic, cl is the load capacitance, so we can ignore the cgs. So gm1 gm2 ratio, and then cl over cc ratio. That is how I end up having this term over here. Okay. Now the final one, due to the right half plane 0, omega k again, gm1 cc. Now the 0 frequency is given by gm2 cc. So multiply by gm2 cc. So cc cc cancel. You actually have the ratio of gm1 over gm2. So now it actually gives you a design equation. Using this design equation, what phase margin do you need? Suppose I need 60 degree. I just have to play around with the parameter. How do you pick gm1, gm2? How do you pick cl, cc? So that after 90 degree, minus it gives you 60 degree. So it tells you this whole thing has to be contribute about 30 degree, right? And then you can pick gm1, gm2 accordingly. I don't know whether you guys recall, during my lecture 3, at the very last example of M, I always mention gm2 need to be bigger than your gm1. You can go back and refer to my, revise my lecture 3, the last example when we talk about OM design. At that time it tells you, we always use that, but just accept as it is. I never explain. Actually looking at this guy, now you know why. If gm1 less than gm2, this phase margin, you are going to have arctangent less than 1. So the phase that you can contribute will be less than 45 degree. Right? Because 1 becomes 45 degree. That is the reason why we want gm1 to be smaller than gm2. In fact, we want gm1 to be much smaller than gm2. Okay? So in OM design, we always do that. So same thing here, you can see, by picking gm1 less than gm2, we also make the phase to be smaller. So you want to make this two phase contribution to be smaller, so that you can have larger phase margin. So the reason why you pick gm2 bigger than gm1 comes from here, the phase margin consideration. So you can see if gm1 less than gm2, it means gm1 over gm2 becomes less than 1, and therefore arctangent give you very, very negligible phase. If gm1, gm2 less than 1 give you negligible phase, it means your phase margin will increase. Okay, will increase. Another thing, your 0 frequency can never be smaller than your second pole frequency. If that is happening, no compensation is possible. Okay, the reason is simple. You can see that omega z1 already contribute minus 90 degree. But where do you reach unity frequency? If you have the 0 frequency smaller than your non-dominant pole, there is a portion of the gain becomes flat before it starts dropping again. So at that time, at this frequency, you can see that it is always bigger than minus 180 degree. Because one contribute by this guy, another contribute by this guy. And before you reach this guy, the gain start to drop, you already reach 180 degree. Because of the phase contribute by dominant pole and the 0. So therefore, the 0 always have to come after the non-dominant pole. Because we want the gain to keep dropping before the phase reach 180 degree. Okay, if you have the 0 happen in between, you reach the 180 degree first before you go to 0 dB. That is the reason why this can never happen. Okay? This also brings another design insight. We want GM2 to be bigger, much bigger than GM1. So if you think carefully, BJT is actually a better candidate. Because in BJT, the GM can be easily obtained because the GM is proportional to current. You just simply double the current of the second stage, the GM double. But for MOSFET, even you double the current of the second stage, you only improve the GM by 40%. Okay? Because it's only improved by square root 2, 40%. So in MOSFET, it's very difficult to make GM2 much, much bigger than GM1. You have to pump ridiculously big current. Okay? So in reality, usually you limit the GM difference to be about 1 to 4. So you pick GM2 to be 4 times bigger than GM1. And the CC, you make it to be about half of the load capacitance. And then you go through the calculation, you find that it gives you phase margin of 49 degrees. Of course, you can play around. For example, let's pick GM2 equals to 5 times GM1, or the CC to be smaller than the CL, let's say by 1/3 or 1/4. You can probably improve the phase margin a little bit. Okay? 50 degree, there is a picking. There might be some ringing. Okay? But if that is the only thing that you can do, you can accept 50 degree because it's still considered stable. So this is all lag compensation. Lag compensation meaning that you basically just either introduce the load capacitor or introduce the Mueller capacitor. Okay? Are we able to cancel away the right half plane 0? This principle come about because if we look at the total phase margin contribution, there are 2 terms. One is due to the non-dominant pole, we cannot get rid of it. The system always have non-dominant pole. But this right half plane 0, is there a way to cancel it? Because if you cancel it right away, you don't have this guy. It's much easier to achieve 60 degree phase margin, right? So can we do that? So it turns out we can. We can introduce one additional register in series with the CC over here. So if RZ equals to 0, we actually go back to the previous one, the previous Mueller compensation. But before we do that, let's see how can we derive the 0. So we apply the same concept. 0 means at the frequency omega naught equal V naught equal to 0. So if V naught equal to 0, because this is also ground, so I don't care about the RL2. Now this current source is going to be GM2 V1. So I can write it over there. And the V1 is simply given by, where is the V1? GM2 V1. This current is given by V1 multiplied by the impedance of this guy. Not impedance, admittance of this guy. So V1 multiplied by admittance of this guy will give you the current. So V1 multiplied by this admittance will give you the current for this guy. And this current will be exactly equals to the current due to the transistor, GM2 V1. And then you can see V1 cancel. And eventually, if you want to find the 0 frequency, you just substitute S equals to J omega 0. Okay? And if you do that, eventually you get the following. And the omega Z1 now got the following expression. If RZ equals to 0, okay, it reduced to exactly what we have before. Now, if RZ equals to exactly the same, 1 over GM2, so now you can see the omega Z1. If RZ equals to this guy, then this whole thing becomes infinite. Effectively, you are cancel away the right half plane 0. The 0 frequency happen at infinity. Now, if RZ is bigger, If RZ is bigger than 1 over GM2, now this guy becomes negative. So instead of having right half plane 0, now you actually have left half plane 0. Left half plane 0 is good. Why? Because left half plane 0 introduce phase lead. Remember, all the trouble about stability is because you keep introducing phase lag. So you reach 180 degree. But if you are able to introduce phase lead, I will be moving further away from 180 degree. Okay? So this is what we had before. Although it can help, we can still design stable system, but not as good. This help you remove the additional phase contribution. So that is good. It will help you improve the phase margin. This is even better. It not only remove, it do more than that. It introduce phase lead. So you make the system having better phase margin. So if we apply this guy, this is what we call lead lag compensation. Lead lag compensation. If you apply this guy, it becomes lead compensation. Now effectively, if we cancel away the right half plane 0, it becomes a 3 poles 1 0 system. So for moderate RZ, okay, the third poles move very far away. Since the third pole is very far, we don't care. It is not going to affect the system. The two dominant pole is very similar to the case where RZ equals to 0. That's good. We already know how to do that. The first dominant pole is Mueller effect. The non-dominant pole is basically consider the Mueller capacitor short circuit, and then we have two capacitor multiplied by 1 over GM. Okay? So that's good. And then the only thing that can be manipulated is the 0. So depend on the RZ that you choose. I can make the 0 happen at infinity, or go all the way to the left half plane. So the way it works is like you already have right half plane 0 like this, when RZ equals to 0. If you keep increasing the RZ, you go to infinity, positive infinity. But you know, very strange, right? Mathematics. If you go all the way to infinity, you can start coming back from negative infinity. And eventually, it falls under the left half plane. Okay? So how do you implement this register? Of course, you can use ideal register or some passive register. But if you do that, how do you guarantee the 0? Because what we want is RZ equals to 1 over GM2. How do you guarantee that? How do you guarantee that? Very difficult. 1 over GM2 is related to transistor. RZ, if you use a register, is a register. Even I purposely make sure they are matched. Let's say temperature change. Transistor have different temperature coefficient than the register temperature coefficient. So the two register is not going to match over a wide temperature range. Okay? So people introduce or implement the RZ using MOSFET. MOSFET can be a register. Okay? In fact, if you look carefully, because of this capacitor, no current, no DC current can flow through. If no DC current can flow through, this transistor always have to operate at linear region. Do you buy that? If no DC current, transistor has to be operating at linear region. Do you buy that? Let's say I have the capacitor. Let's say I turn on this guy, VDD. I can conclude this transistor always in linear region. If you don't trust me, let's assume. You don't trust me. You say, oh, this guy always has to operate in saturation region. If that is the case, the current is going to be half mu n COX W over L VGS minus VTH squared. Agree? But where does the current go? It cannot go anywhere because this is open circuit. So that means it contradicts. If you assume transistor in saturation region, you come to the conclusion it has to be a current source. If it's a current source, you have to flow somewhere. But the circuit tells you nowhere to go. So it means your assumption that it is saturation region has to be wrong. If that is the case, how about linear region? The current becomes mu n COX W over L VGS minus VTH, and then VDS minus VDS over 2 squared. This is linear region equation. Now, can this guy become 0? Possible. Although VGS minus VTH is not 0, but if VDS equal to 0, this guy equals to 0, the whole current is 0. Right? So linear region assumption fit. And the VDS happen to be 0. So now, with this configuration, you know that this transistor always in linear region. If it's in linear region, it behaves like a resistor. Okay? What is that resistor value? So we can calculate. To find out the resistor value, you can use the linear region equation. ID equals to mu n COX W over L, and then VGS minus VTH, VDS minus VDS squared over 2. Now, to find the resistor, you should find delta ID over delta VDS. Right? So, if you assume the VDS is so small, you don't even care about this term. If you find delta ID over delta VDS, basically, you just remove VDS. And that is how you end up having the following. Right? So it tells you the conductance is simply given by this guy. What is GM2? GM2 is based on half mu n COX W over L VGS minus VTH, the whole thing squared. So if you find delta ID versus delta VGS, we go through that already, you also end up having the following. Your goal is to make RZ, which is given by 1 over G DS3, equals to 1 over GM2. In short, we just need to make sure GDS3 equals to GM2. To do that, you only need to make sure this guy equals to this guy, because mu and COS cancel. Okay? The only difference is that I can make M3 equals to M2, but how do I make this guy equal to this guy? Okay? In particular, what is VGS3? If you look at the VGS3, it's actually equals to VGS2. Sorry, I'm wrong. Let me see. VGS3, where is VGS3? VGS3 is here. Okay? Is given by VB subtract away VGS2, which is here, VGS2. Okay? Not only that, your threshold voltage, VTH N2 and VTH N3 is not the same. Because VTH N2, you can see there is no body effect. But VTH N3, there is actually body effect. So it seems like not that easy. Even I try to make this circuit, it doesn't actually make GDS3 equals to GM2. But it turns out circuit can do the trick. So here is a simple circuit to make sure this transistor track this transistor. So how do we do that? Now, first of all, we are applying VGS2 to this transistor M2. We can apply the same thing. This is again the concept of reciprocal bias. Okay, you are replicating the VGS to the other guy. So if this guy draws certain current, you apply the same VGS, this guy also draws the same current. Get the point? Forget about the ratio first. You just think in terms of they are equal sizing. I can guarantee this transistor and this transistor having the same current if they are having the same sizing. Now, if they are having the same current, I mirror this guy. So let's say this is ID. So this is also ID. I mirror this guy, this is also ID. Agree? And this ID flow through this guy. If I pick this transistor exactly the same, this is also ID, isn't it? Yes? Now, if they are the same, that means this voltage is also VGS2. Right? Because same current going through the same transistor. So if the transistor have this amount of current, it has to have this amount of VGS. So by doing this, although they are not the same circuit, but I seem to replicate the busing condition. So I establish the VGS2 over here. Now I stack on top a transistor M3. This transistor M3 stack on top is going to generate a VB. I then use this VB to control this transistor VB. Sounds complicated, but let's see what does it bias. Okay? One thing is, you notice, now I guarantee the same current will flow through M3B and M2B. If you recall, Gn equals to square root mu n COX W over L ID. Right? So GDS, you can also do something similar. Mu n COX W over L ID. They are identical. So if you guarantee the same current, the transistor sizing also identical. You can guarantee GDS equals to GM, right? You don't even care about what is the VGS, what is the VB. You guarantee the current flowing through the same. They will exhibit similar GDS and GM. And that is the beauty of this circuit. By mirroring the current for ID2, I force this current to go through this transistor and this transistor. So by doing that, I'm forcing these two to have the same GM. And you are using this transistor to control this transistor. Due to the reciprocal busing, both should have similar GM. That is the beauty of reciprocal bias. Okay? So by doing that, we are able to make this transistor track this transistor. If you are able to track, you cancel away the right half plane zero. That is the beauty of this method. Another method, the reason we have right half plane zero is because not only we have the feedback, we also have the feed forward. So by using a capacitor, and resistor, not only with feedback, that is what we want. Mueller effect, feedback. But there is also the path can also go the other direction. It's bidirectional. And because of this bidirectional, that is how we derive the zero. If you recall, how do we derive the zero? The reason we derive zero is we make V0 equal to zero, and then we assume this current equals to this current, the feed forward path. Now, if we don't allow this current to go in this direction, we don't have zero. So how can you do that? Have the feedback, but no feed forward. Introduce a buffer. By introducing a buffer, you take whatever the voltage, you feed back to this capacitor, so the Mueller effect still exists. Okay, the Mueller effect still exists. So you still have the dominant pole, you still have the non-dominant pole, okay? But at the zero, what happened? So at the zero, V0 equals to zero, okay? This guy also zero, so RO2 useless. RO2 useless. Now V0 equals to zero. Any current that can flow through here? If you think carefully, this is zero. The resistor, no current can flow through. Over here is connected to the gate, which is open circuit as well. So no current can flow through, which means no current can flow through. The Gn V1 has to be zero. Gn V1 has to be zero, it means V1 has to be zero. So if V1 has to be zero, it means this point has to be zero. Okay? This can only happen if the impedance is 0. So whatever the current you go through the register short circuit becomes 0, therefore no voltage can exist. So how can you guarantee that? If you look into the impedance as 1 over SCC, and then you look into this impedance, 1 over GM3, if this impedance becomes 0, then whatever that we describe here, valid. And if you do that, you find that your 0 frequency is actually now becomes left half plane 0. It's no longer positive, it's actually negative. We already covered that. Left half plane 0 is okay, because it doesn't introduce phase lag. It doesn't introduce additional phase lag that contribute to that reduce the phase margin. So left half plane 0, which introduce phase lead, positive phase, that actually help improve the phase margin. So let's go through the OM composition example. We covered this in lecture 3, so you can refer to lecture 3. We go through all these small signal parameter like GM, R0, and then at that time I told you make sure GM6, this is the second stage, second stage GM. This is the first stage GM. Okay? Same as the example that we talked about. So I'm making the second GM larger than the first GM. At that time I didn't tell you the reason, now you know. Because of the phase margin consideration. Now, initially, let me see. Okay, the frequency that we have, dominant pole is 63K, non-dominant pole is 65 meg. The 0 is about 400 meg. We go through this frequency response before. So lag compensation. So for lag compensation, basically, we can consider the CC cases. So let's say you run the simulation. You build all these things, you run the simulation. And you got the following gain response and the following phase response. Your calculation tells you your phase margin is about 44 degrees. Okay? And your unity gain frequency is 71 megahertz. 44 degrees is not sufficient. You want to target it for 60 degrees, for example. So what can you do? What you can do is, based on the simulation, let's look at 60 degree phase margin. Means my phase has to be 120 degrees. Agree? So you go through the phase response, you identify 120 degrees, probably somewhere around here. Minus 120 degree phase margin. You look out the frequency. Okay? And you find that to get phase margin of 120 degree, the new unity gain frequency has to be 43 megahertz. So based on this guy, you can then calculate. According to the unity gain frequency is given by GM1 over CC. Okay? GM1, we already know from the small signal parameter. This is going to tell you the new CC. And the frequency we are obtaining from the simulation. The original simulation have the unity gain frequency at 71 meg, but the phase margin is only 44. So we identify 120 degree. What is the new frequency? We make that frequency becomes our unity gain frequency. And that turns out CC has to be 8.8 picofarad. So you rerun the simulation with the new updated CC, and you can see that now phase margin is close, 58 degree, very close to 60 degree, and the new frequency is actually 33 megahertz instead of 43. Okay? Calculation, there are some approximation, but that is how we can obtain the new compensation capacitor. Okay, just based on the simulation, pick the right frequency, what is the corresponding phase that we want, pick the right frequency, and calculate what is the CC to give you the desired frequency. Now, lead lag compensation, so we can build the same circuit, but instead of having just CC, we insert a transistor. In the example, we use NMOS. In this case, we use PMOS, but the concept is the same. You can see that this guy have this transistor stacking with this transistor. So you are going to build a current mirror that actually have this transistor stacking with this transistor. The M6A will track this guy, M9A will track this guy, and they will have the same current flowing through. And this current is actually the same as this guy. So it's actually the same concept. By doing that, you are able to track the zero, and therefore we have the lead-lag compensation. So let's see by doing that, what is the frequency that we are getting. So we still use the original parameter. So from here, we can see that the phase margin improved to 54 degree compared to the previous one, which is 44 degree. That is about 10 degree improvement. And the cutoff frequency, the unity gain frequency, is 68 megahertz. Okay? Now, if we are not happy with this one, we want to have phase margin of 60 degree, so same thing. Let's look at minus 120 degree. What is the corresponding frequency? And we find that the frequency that gives 120 degree phase shift is 52 megahertz. So with this guy, we can do a calculation, same thing. Now we equate this guy equals to 52 megahertz. Your CC is no longer 8.8 pico. You only require it to be 73. So if you go through the calculation, you find that you over-designed it. Your phase margin now is 67 degree. Okay? Your unity gain frequency now is 44 megahertz. Okay? So what you can do iteratively. So now you do the same. This is too much. So let's identify 120 degree. What is the new frequency here? Okay? You do it a few times. Eventually you reach 60 degree. But the bandwidth is going to be bigger. So that is the beauty of lead-lag compensation. You get higher bandwidth and better phase margin. I'll stop here. We'll resume at 7:50, and then we can continue cover the lead-lag compensation. I also make the announcement talking about the one additional library, right? I think that is required in Prof. Ma portion for the project. This one. Okay, you just have to edit the cds.lib and include this statement under maybe the last line of cds.lib. It will include one important library called AHDL-lib. AHDL-lib. Why that library is important? Because it gives you logic gate. You don't have to design your own logic gate. You can use AND gate, OR gate right away. Why? But I remember this announcement come earlier than you approached me. 25th March, right? You approached me last week. So this is, yeah, correct. I make this announcement because Prof. Ma asked me, why students last semester can access the AND gate and this semester cannot? Because last semester we didn't use any PDK, so we include different set of library, so that happens to be there. This semester, we use the PDK setup, and that setup doesn't include the AHDL-lib. So you include this segment, you have AHDL-lib. What else do you need? I think there is some behavioral OM model. In the AHDL-lib, you can directly use it. I hope the message didn't come too late. Is it too late already? So you guys don't know what that is. I thought I mentioned this already. AHDL-lib. If you have built your own logic gate, that's also good. Any of you are doing IC design? Anyone in the IC design industry? No? Then why do you pick this module? going to. Depends on your level, because I think the reason we bring in Prof Ma from industry is because he can talk about some of the topic that the industry is doing. I don't know whether that part is helpful. For my part, it's more basic, but I don't know. One of the things I find is that a lot of engineers nowadays, they just rely on simulation. Meaning that you give them something, they probably grab the circuit from the paper and they just run the simulation. If it works, it works. If it doesn't work, sometimes they also don't know how to decipher. So, I don't know. That's my own feeling. Okay, I think today we are going okay. So should be able to...
Recording in progress.
Should be able to finish earlier. Okay, so we have covered two conversations. One is lag. The lag got two methods. One is just simply shunt. Another is using Mueller. Okay, and you probably know by now, using Mueller allow you to do the pole splitting. The good thing is capacitor required is smaller, and also the frequency bandwidth is wider, okay? And mid lag is even better. You totally cancel away the right half plane zero, so remove the phase lag. So therefore, you also allow you to get good phase margin, smaller capacitor, and also wider bandwidth. Now, can we do better? So if you think carefully, if I'm able to cancel the zero, that's good. But if I move the zero to the left half plane, that can help contribute phase lead. But what if I choose the zero in such a way that it exactly cancels away the non-dominant pole? Will it be even better? Originally, I got two pole. Two pole contribute to 180 degree, right? Because one pole contribute 90 degree. You have two pole, it contribute 180 degree. That is the problem that gives rise to the stability. Now, if I have one left half plane zero, I can tune the value such that it can cancel away one of the pole. I will be able to reduce the whole system into just one pole system. One pole system, always stable. Am I right? Because the phase lag is only 90 degree. No matter what, you always get 90 degree phase margin. So that is the theory behind. So if you make the zero equals to the omega P2, the non-dominant pole, so the zero is given by this formula. Now we want to make sure it equals to this guy. After some manipulation, your zero need to be exactly this guy. Is it easy? Is it easy? Can it be done? If you think carefully, we already figured out a way to make RZ equals to 1 over GM2, right? So what this guy is telling you is basically just multiply by certain factor. Am I right? Can this factor be accurately controlled? Possible. Why not? The beauty about capacitor nowadays is that you can make it ratio. If you, let's say, pick CL equals to, let's say, 4 times CC, so what you're going to have is basically 5 to 1, right? 1 over GM. So 1 over GDS equals to this guy. Am I right? On chip capacitor, you can always pick it in such a way that you can ratio it in a very precise manner. And then we already figure out you can actually make this guy to be equal. So in theory, it's actually possible. It's actually possible to do that. In theory. In reality, you are going to have some trouble, okay? Because you know, no matter how good you are, you cannot get exactly 100% match. There is always some mismatch. In design capacitor, let's say you can get 1% mismatch. That is considered very good already. Now, if you design very high resolution ADC, you can probably get down to 0.1% mismatch. Okay? All these require you to use large area devices. Because the larger the area, the better the matching. So that is the de facto rule of thumb. So it's possible, but no matter how good it is, there is always certain percentage of mismatch. So which means, if you are not able to make them exactly equal, you might not be able to cancel them fully. If you are not able to cancel them fully, you might have trouble. That will give rise to the so-called doublet. So doublet arise because we cannot fully cancel them. We appear to be fully cancelled, but it's not fully cancelled. I'll highlight that point. Okay? So, if supposedly you are able to estimate CC and CL in a ratio, okay, then you can actually choose this design accurately, but to be frank, no matter how good you are, you cannot make it exactly match. So as long as there is a 0.1% mismatch, you don't get fully cancelled. I give you an example. Suppose you have S minus, let's say 0.01. And then the denominator you have S minus 0.01. They will cancel. But let's say it is 0.001. Will they cancel? In the past, I will tell you they are approximately equal, so cancel. Unfortunately, the system doesn't work that way. They appear to be cancelled, but they are not cancelled. And that gives rise to the so-called doublet. And think about that. The whole thing about compensation is to make sure the capacitor can be lowered, the bandwidth can be widened. The reason we want to widen the bandwidth because we want it to settle faster. But the existence of doublet exactly against it. If you are able to remove everything perfectly, there is no doublet, you get the settling behavior that you want very fast. But if there is a doublet, the system can actually settle very slowly. So the thinking that I get a wider bandwidth doesn't really help. So here is the example. Supposedly you can make CL equals to 10 picofarad, CC equals to 4 picofarad. So RZ equals to exactly 3.5 over GM2. Okay? And we already know we can actually pick the transistor ratio, okay, in this manner. And then we can actually achieve the lead-lag compensation. And then you can see, not lead-lag, the lead compensation. And you can see that this whole thing appears almost like a single-pole system. Right? This is a single-pole system that dropped with minus 20 dB per decade. And you only have minus 90 degree phase shift. And your phase margin is very, very good. Almost close to 90 degree. Okay? In reality, by doing this, you get very good phase margin, 72 degree. You don't need that. Okay? So you can actually widen the bandwidth, make it move to the right. So here we find that if I want to go to 120 degrees, so I look at this point. So I look up, okay? I find that to get 60 degrees, my new frequency is actually 132 megahertz. Compared to this simulation, 87 megahertz. So now you are able to widen the frequency further to 132 megahertz. So by doing that, you can see the required CC also very small, only 2.9 pico. So if you update the whole design, now the ratio becomes 4.5 over GM2. Okay? And with the new simulation, you get exactly 60 degrees. The frequency now becomes 117 megahertz. You might be thinking, I'm lying, because just now I told you, the zero cancel with non-dominant pole, I only get one pole system. So the whole thing should be 90-degree phase margin. But don't forget, when we estimate the system, there is a lot of parasitic we didn't consider. So this is not a simple two-pole system. The reason it is two-pole system is because all the other poles happen far away. So it's like there are very two big guys exist in this room. My whole attention only focus on these two guys. All the rest, too small. I don't care. But once I remove these two guys, you guys become significant. You get the point? Okay? So that is the reason why you can never get 90-degree phase margin. When you remove this, something pop out. Okay? But that is good because that something pop out is so far away. So that allows you to widen the bandwidth further. Now, let's look at the transient response. We haven't covered about the doublet. We will talk about the doublet later. So transient response. This is the original OM. Okay? And we talk about this is the loop gain. So if you use the loop gain of 1 plus T0, you are able to widen the bandwidth up to this point. Okay? So the closed loop transfer function, if you rederive it, you'll find that the original bandwidth is 1 over tau naught. But with the feedback, you lower the bandwidth to, not lower, increase the bandwidth to 1 over T0 over tau naught. So you widen it by a factor of 1 plus T0. That is the beauty of feedback. You are trading off the gain with the bandwidth. You make the gain lower, so you drop the gain. But effectively, you widen the bandwidth. And we know the bandwidth is somehow related to the settling time. Okay? Settling time. So you also improve the settling time by this amount of factor. Now here, why do you call it linear settling? If you understand this system, you know that the way it's settled in the step response is going to be settled like this. Exponential. Exponential is not linear, right? So this linear settling is more referred to, this is the linear system. So settling behavior of linear system. So we call it linear settling. So here, if you use it in a feedback manner, so this is actually a unity gain feedback. Okay? When you input the step response, so you go and calculate this guy. So you find that the settling behavior is given by the following. Okay? There is a tau over here. But this tau is now widened by the bandwidth. The loop gain of this feedback configuration. So a very famous equation, 6.9 tau, that is based on the assumption that the settling behavior will settle to 99.9% of the final value. So the error is only 0.1%. So if that is the case, example, if you derive the 3 dB bandwidth to be 100 megahertz, okay, then you can find out the settling behavior to be 6.9 over omega 3 dB, which is given by about 11 nanoseconds. That is how you calculate. Now, what is doublet? If I was able to cancel this guy perfectly, I will get this guy, which is a one-pole system. Right? There is only one pole here. The rest, 20 dB per decade. No other pole, no other zero. Perfectly cancelled. But if there is a mismatch, which is easily happen, so this guy appear to be cancelled, but they are not cancelled. So let's say it happens somewhere around here. The omega, the pole, second pole, and the zero frequency are so close. You are going to end up having two scenarios. One is like this, one is like this. One is zero happen before pole, another is pole happen before zero. Okay? So if zero happen before pole, you will see that it goes flat first before it go down. If pole happen before zero, it will go down steeper and then regain the previous slope. But no matter what, because the two frequencies are so close, if you zoom out, you don't see it. You don't see it because it's like you look at the slope. You look at this portion. You look at this portion. This is so small. You hardly notice the discontinuity. So to you, if you zoom out, you see almost look like this. So it appears to be cancelled, but it's not cancelled. It's still there. Okay? So if you are not fully cancelled and it's still there, and these two are so close, this is what we call doublet. Doublet. It doesn't matter whether it's this case or this case. These are all doublet. So now let's take a look. If there is a doublet, what is the impact on the overall frequency response? Now, without doublet, you only have dominant pole system, one pole system. So if you do a feedback, okay, it becomes following. You do some manipulation, following, and you can see that the bandwidth actually get widened by T0 factor. You already know this, right? So that is without doublet, everything cancels perfectly. We get what we want. We widen the bandwidth by T0 factor. Okay, that is desirable. And you will get settling behavior also improved by the T0 factor. That's good. Everything is good. But now let's see. If I cannot fully cancel, I have to keep this term, I have to keep this term. No matter how close they are not perfectly matched, which means that you cannot fully cancel. So it's always there. If you apply the feedback factor, you're going to end up having the following. Very complicated. Let's do some massaging. You get the following. Okay? And then, because we are interested in the frequency that is very close to the 3 dB, so we can assume the frequency is large, much larger than this dominant pole, so I can drop this term. So I end up having the following. Okay? And now, I take out this guy. I take out this guy to the front vector. So the A0F, after you're taking out, cancel with A0, I get this 1 over F. Now, if you take out A0F, this is actually T0. So you can see this omega P1 get improved by T0 factor. This is not surprising. It's still what we want. But we have this nuisance over here. So we can do further thing. Okay? So at frequency that is very, very close, in between the non-dominant pole and the dominant pole. Okay? Now the non-dominant pole and 0 are very close to each other. So in this frequency range, I basically don't care about these two terms. Why? Because you can see when the frequency is smaller than omega P2, so this is ignored, I get back to only this term. So it behaves what we want, a dominant pole system. But for frequency that is bigger than this guy, we can do some simplification. So now if this frequency is big, we know this whole thing, this whole thing, including this guy, is going to be much bigger than 1. So let's ignore 1. And we are going to end up having this guy flipping. Okay? So now, when this is big, whether I add in 1 or not, it doesn't matter. But add in 1, it allows me to analyze this thing in a much easier manner. So once you have this thing, you relook at it. I can actually factorize it into 1 over S plus T0 omega P1 plus 1 plus, let's say, K1. K2 S over omega P2 plus 1. So you actually have two settling behavior. One is this guy, another is this guy. Because this will allow you to settle according to minus T T0 omega P1. This guy will allow you to settle according to exponential minus T omega P2. Okay? So with this system, you actually have two settling behavior. This guy and this guy. And they are not going away. The omega P2 didn't get cancelled. They are not going away. So if you think now the settling behavior get widened because of this T0, might not be the case because omega P2 could slow down. Okay? The only way you can avoid this is to make sure that this thing is still much smaller than this guy. So the settling behavior is still dominated by this guy. Okay? If not, you are going to end up having something like this. So without doublet, this is what we expect. Green curve. It settles very fast. Okay? But with the doublet, you see that initially it settled quite fast, but once you try to reach to the settling behavior, the second pole come into effect. And you don't actually get settled to 99.9%. To settle to 99.9% is here. You can see that this is 99.3%. From this onward, to get down to 99.9, it takes forever. That is the issue with doublet. Okay? So to be frank, lead compensation sounds good in theory, but you know, impossible. Even I can make the register to be perfectly cancel ratio, but you know that cannot happen in reality. It doesn't matter whether the temperature track, okay, or whatever, the sizing ratio track, but no matter what, you cannot make two twin identical. I mentioned these, two twin, can they be identical? You count the number of hair they have, they will be different. Okay, they cannot be identical. And because they cannot be identical, they cannot cancel. If they cannot cancel, you will have doublet. And this doublet, you have to be careful. If you are not careful, instead of speeding up the response, you could be slowing down the response. Now, nonlinear settling. Nonlinear settling go like this. If this whole thing is a linear system, the settling behavior is well predicted using 6.9 tau. So this behavior, 6.9 tau, is basically based on the exponential settling behavior, RC time constant. So that is well known. But let's say you want it to settle in the exponential manner, but the OM, you limit the current. Because any design, OM, you by now you know, you always determine what is the tau current. So when you try to switch from one side to the other side, the current is actually fixed. The current doesn't increase. Because when you switch the voltage from one to the other, you basically just steer the constant current to either this path or the other path. So the amount of current that you can achieve is always constant. So if that is happening, you are going to have the so-called slew behavior. Slew behavior. Now if you look at the settling behavior for this slewing, very strangely they look very linear. It's actually linear slewing. The reason is very simple. Because C d v dt equals to I. I is constant. So therefore dt equals to C dv over I, constant. So you can see that the linear time, if you have constant, so the voltage actually increase linearly with time. Simple as that. So it actually appears to be linearly increasing with time. But we don't call this kind of settling behavior linear. Because when this is happening, what you are going to have is a non-linear system. Non-linear system. A simple understanding, why do we call it non-linear system? Think about that. An amplified, it will go like this. But let's say the supply up to here, we are going to end up having this is non-linear behavior. Am I right? The voltage gets clipped. So in a similar manner, your current is no longer what you want or give you. Your current gets clipped. When you change the voltage so much, the current already reached its maximum, is saturated. And that clipping behavior result this system becomes nonlinear. So any settling behavior comes from this nonlinear system is called nonlinear settling behavior. Okay? And the total settling behavior, if you think about that, it actually consists of two parts. The first part, slew. So when the voltage difference is so big, the current get clipped, only slew behavior happen. So only when the voltage reduced to some reasonable range, the linear system start to creep in, then you have this P-linear settling behavior. So the total combined time is going to have both the P-slew and T-linear. And it's going to be longer than your linear settling behavior. So slew rate, just to explain a little bit, what do I mean by current get clipped? Now you see, this is a two-stage amplifier. This is the first stage. This is the second stage. We design the first stage. The differential pair always have this constant current source. So when you are switching, let's say V plus bigger than V, let's do V plus smaller than V minus. Now initially, if the difference is not that big, you can see the current actually changing according to the voltage. But as soon as the V plus is much bigger than V negative, much smaller than V negative, then right away, all the current flow in this. If the current flow in this, it means that you already reached the maximum current, which is 1 milliampere. It also means that how much current is available to charge this CC? Only 1 milli. I cannot go more than 1 milli because it's limited by this tau current source. So if you happen in this range, your current actually is a linear system. It will change according to the voltage. But once you reach this range, your current becomes constant. And you will not be able to charge or discharge the circuit according to the voltage difference. So that is when the clipping happens. Now this is easy to understand. Okay, for this guy it's easy to understand. It's limited by this guy. You can see the current here is constant, either 1 milliampere or minus 1 milliampere. So either the current flow from here, or in other cases, let's say the current all go from here, you get mirror, and there is no current here, so the current go in this manner. So it's either 1 milliampere or negative 1 milli. Understandable? Now when you have two-stage amplifier like this, okay, so let's take a look. If my V plus is bigger than V negative, let's see what happens. So you are going to have all the current flowing here. Okay, all the current flowing here. So this voltage is going to go down. If this voltage is going to go down, you are going to have bigger current going here. If it exceeds 1 milliampere, you are going to charge out the CL. Okay, you are going to charge out the CL. So you are going to have 1 milliampere, but you see that the slope is not exactly constant. So the reason is simple. You can see that the current is not exactly constant. If the voltage can go down, go down, go down, my current will keep increasing, increasing, increasing. So you will not be exactly flat. It's not constant. You are still increasing slightly according to the voltage. Okay, but it's still nonlinear nevertheless. But if let's say V negative is bigger than V plus, so now all the current flow here. Okay, if all the current flow here, so all the current flow here, eventually this guy will reach VDD. If you reach VDD, no current. If no current, you have 1 milliampere to discharge the capacitor. So therefore, this current is constant over there. So if it's settled exponentially, the system is linear, so linear settling. If the settling behavior is limited by current, you have the so-called slewing behavior. So here is some example that I taken from some paper. So how do you know that a system is actually slewing or not? Very simple. Observe the step response. So if the input is like that, you look at the output, you look at this guy, it's settled linearly, not settled linearly. The slope is linear, this guy is actually slewing. Okay? If it's not slewing, it will behave like this. Okay? When it is exponentially decay, exponentially rising, we know this is linear behavior. So to estimate the slew rate, we just try to figure out how fast can the voltage changes. We are using the capacitor equation, C dV dt equals to I. So therefore dV dt equals to I over C. So if the current is constant, capacitor you know, you can actually estimate the slew rate. So the slew rate is basically given by the maximum current divided by the available capacitor that you want to charge. So in this case, let's say the cal current is 1 milliampere, the capacitor is 4 picofarad, that give rise to about 250 volt per microsecond. That is the slew rate. So the slew rate, the settled behavior will be given by the slew time plus the linear time. Linear time is 6.9 tau. That is easy. But so tau is related to bandwidth, omega bandwidth. Okay. The slew time is basically the voltage step that you want it to rise divided by the slew rate. Okay. So here from the example, this system has a bandwidth of 100 megahertz. So if you go and calculate 6.9 tau, we just now calculate is about 11 nanosecond. And then this guy will give rise to another kind of second, so you add them together, they actually give you longer, about 15 nanosecond. Now, slew rate, if you think is just about settling time, but if you think carefully, it's actually more than that. Take an example. If I have a sinusoid, if you try to find out the gradient, you see that the maximum gradient happen at this zero crossing point. So if you find the ddt, actually this is the peak of the slope. The peak of the slope is given by omega v naught. Omega v naught. Now, if the maximum current is constant, okay, you go through the C dV dt, and the slew rate is given by this guy. You want to make sure that this slew rate is actually bigger than the omega v out max. If it's not, you are going to end up having distortion. Okay, shown over here. If your slew rate is actually smaller than your frequency multiplied by your output voltage, you are going to end up having a triangle wave. Not that difficult to understand because you can think, this is the maximum slope. But what does the slew tells you? The slew tells you, I can only climb at this rate. You get the point? My sinusoidal demand me to go in this way. But the slew tell me, I can only go in this manner. Right? So because of this, my sinusoidal will not be able to rise according to what I want. It can only rise according to what I can get. So that's why you end up having a triangular wave. Okay? So distortion will happen. If the slew rate bigger than omega v naught, then no problem. You will get the sinusoidal. Now there is another common mistake that students make. I remember my professor, when he teaches this subject, he specially set this question. And I remember in my class, less than 10% students get it right. So he basically give us the op-amp, he give us the feedback factor, the GBW, everything, and then he asks us what is the maximum frequency and also the slew rate. He asks us what is the maximum frequency this op-amp can handle. A lot of students, they just look at this guy. Okay, I have omega naught, but I'm widening it by the feedback factor, so it becomes T naught, right? So let's say originally the bandwidth is 1 megahertz. Due to this loop gain, I increased by 10 times, so now I can handle 10 megahertz signal. A lot of students do that. But once they throw in this slew rate behavior, they find that it can only handle 100K. 100K. So this is a very common issue that students ignore. They think that frequency behavior is only related to bandwidth. But for op-amp, the slew rate can also affect how high the frequency that it can go. A lot of students think slew rate is only related to settling behavior, but it actually can affect the signal distortion. So when you look at the op-amp, to determine the maximum frequency that it can operate, you always have to look at two factors, bandwidth and the slew rate. And then you pick the smaller one. The smaller one is going to be the bottleneck. Okay? If you can meet the slew rate, then closed loop bandwidth is going to be the bottleneck. But if you cannot meet the slew rate is going to be the bottleneck. With that, I'll end today's lecture. Good, today end earlier to compensate the late lecture for the previous 2 weeks. Any issue? So remember to hand in the homework too. Any question about the homework? No, right? Project? Not Prof Ma project, my project. Haven't started. Prof Ma project, got issue? Okay, good luck.